Okay, then. Thank you. And so this morning we introduced ourselves to the notion of a Fourier series, and we took our time about it. We motivated it with reference to Taylor series of functions, expressing functions as infinite polynomials, or approximating them with longer and longer, higher and higher degree polynomials. We also reminded ourselves of some basic ideas about vector spaces, bases for the vector space, and thinking in terms of kind of simple 2- and 3-dimensional vectors. Reminded ourselves of the roles of the dot product and how the dot product is related to the coefficients that arise when you express a vector as a linear combination of basis vectors. I won't revisit all those things now, but I'll refer to them again and again as they arise. So we'd like to get a little bit more practical with it now and look at some initial properties and hopefully an initial example of working out a particular Fourier series. But first of all, is there any questions from this morning? Anything that you'd like me to clarify or speak to again? As usual, my visualizer pages are in the comments to the YouTube video, and there's also a link to that interactive stage cell thing, which was demonstrating the Fourier series of the square wave function. So if we look to our notes, first of all, on the first page of chapter 3 there, here in 3.1, we've got the basic existence statement of the Fourier series. We'll be doing somewhat of providing some justification for this. We won't be doing a rigorous proof from the ground up, analytic proof of it, but we will be giving some justification arguments for it. But what it says is this is declaring, this is describing the conditions for the existence of a Fourier series. Okay? Remember, this morning we said all well-behaved functions, nice functions in a way, would have a Fourier series. And this specifies exactly what that nice behavior looks like. Okay? So we're focusing on real valued functions. And we're just focusing on the interval between minus pi to pi. Remember, this is the interval of length 2 pi. And this is because the basis functions we're using, cosine and sine, they are at a period 2 pi. And we may as well choose the interval that's centered on the origin, just for reasons of niceness or symmetry. But this restriction to this specific interval isn't like that much of a break in the whole thing, because as you'll see, you can stretch it out and renormalize it to apply it on any interval whatsoever. Okay, but we're using periodic basis functions, cosine and sine, so the things we're going to be producing are fundamentally periodic. Okay, so we're looking at our objective function f, and provided, well, it has to be these are the conditions it has to satisfy. So it has to have at most a finite number of discontinuities on the interval. So that's good. I was about to say the function had to be continuous. No. So it's allowed to be non-continuous, but just at some finite collection of points within the interval. Okay. So certainly if the function is continuous, then it qualifies. And it's allowed to have at most a finite number of local maxima and minima within this interval. So if it satisfies those conditions, then it's considered, in this context, to be a nice, well-behaved function. And those aren't that unreasonable to ask for. It's a fairly pathological function, which has an infinite number of discontinuities in this closed interval, or has an infinite number of maxima and minima in this interval. fairly strange function that has those properties. So providing that's not true, then the theorem is this existence statement. It says that there exists a set of coefficients, A0, A1, A2, etc., an infinite number of coefficients A, and an infinite sequence of coefficients B, B1, B2, B3, etc., that give you this Fourier series equation. You've seen this equation over and over. You'll be quite familiar with it. So this is the function f is a half, the function f evaluated at x is a half of a0 plus the infinite sum of the cosines plus the infinite sum of the sines. Now we say the function is equal to that. Well, that definition is going to hold almost everywhere. That equality is going to hold everywhere except perhaps at the points of discontinuity. So the points of discontinuity of the function are the locations where the function makes an immediate, instantaneous jump in value. Okay? Now there's a question. So at the point of discontinuity itself, there's some ambiguity about what value the function takes there. Maybe it takes the value that corresponds to one of the branches of the two continuous bits that are stuck together there. But what the Fourier series is going to do, the Fourier series is going to do something nice and fair. It's going to, the value that the Fourier series takes, so the infinite sum on the right-hand side, the value that it takes is going to be the average of the two limiting values as x approaches the point of discontinuity from either side. Okay? So just a quick sketch to illustrate this. These are the two branches of the function at the point of discontinuity. So here's the point of discontinuity here. Then these two values here, this value and this value, so fx plus, yeah, but this is xd, the point of discontinuity. This will be what have I called it, fxd plus. This will be the limiting value of the function as you approach the point of discontinuity from the positive side. This value here will be f of xd minus. This is the limiting value as you approach the point of discontinuity from the negative side. And the Fourier series for this function will kind of do a nice, fair job of balancing those two. So the Fourier series will be coming along here, and it will go up through that point and then continue on there. Something like this, okay? So this quantity here is the halfway point between those two values. So this is that quantity, which is at level half f of xd plus f of xd minus. Now the function f itself might take this lower value at xd, it might take that upper value, or it might take some completely different unrelated value. But what the Fourier series is going to do, as it is approximating the function here, and it jumps up here, it approximates the function here, it's going to go through that distance. And of course, that wobbly red line is just some, that wobbly red line is like the example we looked at this morning. That's some finite approximating Fourier series, not the full infinite sum. If it was the full infinite sum, then it would be would lie exactly over the graph of the original function f. But that's like one of the intermediate finite Fourier series approximations. So we're looking at a bunch of them this morning. Okay. So almost everywhere the function is equal to its Fourier series, except at the points of discontinuity, where the Fourier series does the best job and passes through the midpoint of the limiting values approaching the discontinuity from either side. Okay. Take our time to investigate some aspects of this. And the first thing we want to approach is, so this claim which we declared this morning, and indeed in the linear algebra lecture with the inner products, we saw one instance of it. And this is the claim that this set of functions here, the set of the Fourier basis functions, is an orthogonal set with respect to the inner product. So you've seen 3.4 there, I've called it f here. F is the set of basis functions. Constant function 1, all of the cosines and all of the sines for every value of that integer frequency term n greater than or equal to 1. That's the set of the infinite set of basis functions we're talking about. The inner product we're talking about is the standard inner product for functions on this integral. So it's the integral of the product of values. Okay. And the claim in 3.6 is that the set f is orthogonal with respect to the inner product. Meaning that if you take any two functions from f, take their inner product, you're going to get 0, provided you've actually taken two distinct functions. This is a bit confusing here because phi, we've been using phi in the linear algebra lectures for the inner product. But here, phi and psi are just two functions from f. So phi and psi are a selection of two functions from f. As long as they're different, their inner product is 0. That's the claim. That's what it means to say that f is an orthogonal family of functions with respect to this. So what that means, there's various cases of that to prove. But if we look at example 3.1, it asks us to prove one of these. Okay. So we saw in the linear algebra lecture. So in the linear algebra lecture earlier on, orthogonality for say phi equal to sine of t, psi of t equal to cosine of t. Okay, we saw that example. Here in example 3.1, the notes it's asking us to look at some other cases. So here we're going to let phi of x be the function cosine n of x, and psi of x be the function sine of n x. Okay. So this is one of the cosines and one of the sines. And we're allowing the frequency term there to be different. So we want to prove that these are orthogonal. Okay. So we want to examine, so I'm using the angle bracket notation here, examine the inner product of these two. So by definition, we're using the standard inner product here. This is the integral from minus pi to pi of the product of these two. Cosine nx times the sine of nx dx. Now, and what we did earlier on was we did, see, this is an integral of a product of two different functions. It's not too awkward to deal with. But because it's these nice trigonometric functions, which have nice relationships to each other, there's a standard formula for sine and cosine that will translate this to a linear combination of sine functions. Okay. So the one we're going to use for this is we're going to make use of the formula. Yeah, if you've got cosine of A times sine of B equal to a half times sine of the difference and sine of the sum. Sine of the sum plus sine of the difference. B minus, so it's sine of B minus. Okay, so it's a standard trigonometric relation, and it'll take our product of cosine and sine and replace it with the linear combination of individual sines, and those we'll be able to integrate just using the standard integral of sine function. So this factor of a half we can float out to the front. Remember, integration is linear. We'll park it out here for the moment. So we've got the sine of the sum of these two. So this is going to be n plus n times x. And then you've got sine of the, and it's the one from this original sine function minus the one from the cosine. So it's n minus n times x. Integral of x. Now there's maybe two different cases we have to assume because of this n minus m here. See, if it was the case that n was equal to m, then that would be sine of 0, so that would just be 0, and that would disappear. Whereas if n is not different from m, then we do have a genuine sine function sitting there. So we maybe have to take account of that. So first of all, we'll assume that n is different from m. So there are, in fact, two genuine functions here. Then when you integrate this, okay, well, they both integrate to minus cosines. You get minus the cosine of n plus n times x all over n plus n. You got minus the cosine, n minus m of x over n minus n, closing bracket, and that's evaluated at minus pi. But, okay, so we got to figure out what value this takes. However, you kind of ignore if you just ignore the detail of it for a moment, it's evaluating cosine of a constant multiple of x in both cases, and you're evaluating it at a positive argument pi and at the same absolute value, but the negative argument minus pi. Okay. But remember cosine of y is always equal to cosine of minus y. Okay. Cosine function is symmetric in reflection back the origin. Okay. So it's not really important the detail of having these coefficients here and having these denominators here. When you do the evaluation at plus pi and minus pi, you're going to get 0. Okay. So this whole thing is equal to 0 as required, as expected. Is that clear? Because it's going to be cosine of something times pi minus cosine of something times minus pi. That minus pi, just that minus sign inside the argument of the cosine disappears because cosine agrees. And you're subtracting these values because they're the upper and lower limits of the evaluation, so they're going to cancel 0. So you're just all going to get 0. That's required because what are we trying to do? We're trying to show they're orthogonal. They have inner product 0. So there's the remaining case if n is equal to m. So if n is equal to m, that means this term here isn't really here because it's sine of 0 times x and sine of 0 is 0. Well, that means the integral just becomes 1/2 of this first bit here minus the cosine of, say, 2nx over 2n. But that's just equal to 0 as before as well, for the reason that cosine agrees on plus pi and minus pi, so when you subtract the values, they're going to cancel. Okay, so that proves that if you take one of the cosines and one of the sines, they're going to be orthogonal. Yeah. Any questions about the argument used there, or any clarification I could provide? Now, that's not yet a full proof of orthogonality. There's still various other combinations you might take from there. Okay. So the other cases of orthogonality. So what would they be? They'd be looking at the inner product of 1 with one of the cosines, 1 with one of the sines, or indeed two different cosines, or indeed two different sines. These are all equal to 0. I must say n is not equal to n, so we've got two different cosine functions, two different sine functions. These are the remaining cases of orthogonality that you have to prove whenever you take two different functions from the family F. So these are left as exercises. I think there's some of them specifically named in the in the first set of exercises, but they're all, you know, exercises in integration, basically. It's integrating cosine, integrating sine, or integrating product of two different cosines, or integrating product of two different sines. Okay, that's all about it. Okay, any questions? Okay, so orthogonality says when you take two different functions from F, you get an inner product 0. So what about where you take an inner product of one of the functions with itself? You're not going to get 0 because it's an inner product. You only get 0 in inner product of a vector with itself when the vector is the 0 vector. So these are non-zero functions. So you're not going to get an inner product of 0. But we get some interesting values. Okay. So example 3.2 there asks us to take the inner product of one of the sine functions with itself. Okay. So the inner product of one of these sine functions with itself. So what does that mean? Okay. Again, it's just an exercise in integration. Okay. So nice exercises in integration. These kind of things make it ideal exam questions. We'll see when you look at the past exam papers. So remember, the inner product is integrating the product of the functions. So taking inner product of sine nx with itself means integrating the square of sine nx. And you might regard that as a standard integral, or if not, you can make use of another one of these formulae. It's another double angle formula. Sine squared of something, x, say, is a half of 1 minus the cosine of 2 times x. Okay, so that's good for integration because it replaces the square of sine with just linear combination of the constant and the cosine. And we can just use the standard integral of cosine, yeah, to deal with that. So if we apply that, then we get this factor of a half. We can float out here. And then it's 1 minus the cosine of 2x dx. Okay, so you just go ahead and integrate it. Integral of 1 dx is x. Integral of minus cosine is going to be minus the sine, 2nx, but we've got to divide by that 2n. Application of the chain rule, isn't it? Integrating, you've got to divide by that factor. You're evaluating this between pi and minus pi. Now evaluating x is no problem, just substitute in pi for x. The sine bit, again, forget about the denominator because look, you've got sine of 2 times an integer times pi, or 2 times an integer times minus pi. So these are evaluations of sine at an integer multiple of pi. Whenever sine is evaluated at an integer multiple of pi, you always get 0. Okay? Sine has to be evaluated at a kind of a half multiple of pi. A half integer multiple of pi in order to get a value of plus or minus 1. If it's evaluated at an integer multiple of pi, you get 0. So this part won't contribute anything. You get 0 in both cases. So you'll just be left with a half of pi minus pi. So in other words, it's just pi. No. at 2 pi. Again, the other cases, I won't go through them all. You can also check the other cases for yourselves that if you take the inner product of one of the, sorry, I did the sign, one of the cosine functions with itself, pleasingly, you get pi again. It'd be nice if you took the inner product of the constant function with itself. If you got pi, again, if you don't, you get 2 pi. The integral minus pi to pi dx is the length of that integral, so that's 2 pi. And that goes some way to explain why in the standard form of the Fourier series, the constant coefficient has is just a half. It's rescaled by a half, kind of to make some of the formulae work out nicely. It's just kind of this factor 2 reappears there. So we need to understand all of that, how the inner product behaves on that family of functions. Family is orthogonal, so the inner product is always 0 except when you take the inner product of one of the functions with itself. Take the inner product of two different functions from that family, it's always going to be 0. Take the inner product of a function with itself, it's either going to be pi in the case of the cosine function of the sine, and 2 pi in the case of the constant function. So finally, then, kind of completing the basic story is we're going to, so these are these mysterious coefficients. The Fourier coefficients, the ANs and the BNs, that feature in the Fourier series formula. They're in 3.1. Constant coefficient at half A0, the ANs and the BNs. These have nice formulae, which was given there. Okay, they're giving them all as an integral involving f, and the cosine function for the an, and the sine function for the bn. So in other words, those are inner product formulas. Formulas for the coefficients in terms of the inner product. So looking at section 3.2, that is, you can re-express these things as saying that the coefficient A0 is 1 over pi times the inner product of the constant function 1. The coefficient an is 1 over pi times the inner product of the cosine of nx with f, rather than 1. And the coefficient bn is 1 over pi times the inner product of sine of nx with f. Again, for n bigger than equal to 1. So, sometimes we think in terms of the detailed integrals, other times we just think more generally in terms of these coefficients are inner products of the functions, basis functions with the objective function. Okay? So when you see these things, you're thinking of, remember the example I showed you before, x was a lambda 1 e1 plus lambda 2 e2 e3. The coefficients lambda I were all the dot product of the vector x with the appropriate basis vector. This is what you're thinking of when you see these formulae, okay? Because these are the coefficients in the linear combination of f with respect to the basis functions. The Fourier series equation 3.1 corresponds to this equation for x in terms of the standard basis vectors, and the coefficients there are all dot products of x with the relevant basis vector. And it's exactly the same picture here. f is a linear combination of the basis functions, and the coefficients from that linear combination are rescaled inner products of the function f with that basis function. Okay? So you're all thinking this. Okay? Okay. Now, okay, it looks kind of nice. We've drawn that connection between what we know about simple vectors and dot product, and now this infinite dimensional vector space, infinite basis, inner product. But maybe we need a little bit more. I mean, it looks convincing, but maybe we need a little bit more motivation for this, or a little bit more justification for this. So this is what's suggested in example 3.3. So example 3.3 says, okay, let m be an integer greater than 1. Says use the Fourier series. We kind of have to use the, well, at this level anyway, use the existence of the Fourier series to find an expression for the inner product of f with sine of mx. So sine of mx is one of the basis functions. Find an expression for that inner product and show how this produces the above formula for determining Bn. That function Bn there. Similar argument will persuade you of the functions of the equations for a0 and an. Okay. So if we grant the existence of the Fourier series, this is maybe the little gap in the argument. We're not doing the full rigorous analytical argument from the ground up for the existence of these things. So if we grant that such a thing might exist, such a Fourier series might exist, then this is why that coefficient Bn has to be what we claim it is. Okay? So the example asks us to take the inner product of the function f with this basis function, sine of mx. So this is one of the basis functions. Well, if we're granting the existence of the Fourier series, the natural thing to do here would be to replace f with its Fourier series. So in place of f, I put in a half a0 plus the sum of all the an's cosine of nx plus the sum of all the bn's sine of nx with our only single sine of mx. So the frequency index term on the left is the n. This particular frequency term here is n. Now, what's the first thing we know about inner products? I was going to make a joke. Don't talk about inner products. The second thing about inner products, movie reference, you'll get it eventually. There's the three defining conditions of an inner product. The first one is linearity. Okay, the inner product is linear. Linear, as mentioned in the conditions in the first variable. That can both vary. And what are we looking at? Okay, it's taking up a lot of room there in the first variable, but it's just a big linear combination. Yeah, agreed? Just a big linear combination, doubly infinite, you could say, but linear combination nonetheless. So it's maybe not that hard to think that we could break up this inner product by applying the principle of linearity. So you've got the inner product of 1 with sine of mx. You've taken all these linear operations outside the inner product. So now we've got the summation n equals 1 to infinity, an times the inner product of cosine of nx with sine of mx And then this one, break apart there, is the sum of n equals 1 to infinity bn times the inner product of sine of nx with sine of mx. You have to go carefully with your frequency parameters there. In the first position, they're all n's. In the second position, they're all m's. Okay, we've replaced this single inner product of the big linear combination with this function as now a big linear combination of individual inner products. There's one inner product here, there's one there, an infinite number here, and an infinite number here. Okay? But most of them we know the value of. Okay? Because all of these inner products are an inner product of two of the Fourier basis functions from that family which we call F. At the start there in 3.4. And we explain, okay, we proved some of the cases of it, but we explained that it's an orthogonal family. Okay? So whenever you take the inner product of two different functions, it's always 0. Two different functions from F. So that means most of these are 0. This first one is certainly 0. Inner product of the constant function 1 with sine of mx. Those are two different functions from F. Okay. All of these ones here are 0 as well. So there's the inner product of a cosine function with a sine function. Two different functions in the family F, so their inner product is 0. Almost all of these ones are 0. Because almost all of these is an inner product of a sine function with a different sine function. But there's one which isn't 0. That's when the summation index n here takes on the value n. That happens. Then you're taking the inner product of sine of mx with itself. Okay, that's not 0. But we worked that out. That came to the value pi. Okay. All of the other ones are 0, because they're all an inner product of two different sine functions. So the only thing that survives on the right-hand side is when n is equal to n, you've got bm times the inner product of sine of mx with itself. Agreed? All other inner products are equal to 0 by orthogonality of these Fourier basis functions. So it wonderfully simplifies the thing down from this hugely infinite linear combination of inner products down to just one. And we've already worked out its value. This was pi. So it's bn multiplied by pi on the right. But then you just look at the whole thing. This is the inner product of f with sine of mx equal to bn times pi. So that is indeed the required formula. That the bn is equal to 1 over pi times this inner product, f with the sine mx. Okay, I might have written it before with the f in the second place. Doesn't matter. It's an inner product, real inner product. It's symmetric. And put that in the first place. Who cares? Or in terms of the integral from minus pi to pi, product of f of x times sine of mx dx. Okay, I wouldn't call that full-blown proof of the Fourier series formula, but it's definitely quite a persuasive argument that if the Fourier series is going to exist at all, the coefficients for it have to be as claimed. Bm coefficient is essentially the inner product of f with the sine of mx. Okay, by 1 over 5. Is that okay? Any queries on any of the steps there that you'd like me to clarify? Okay, so as it says there, at the end of example 3.3, a similar argument will produce the formulae for A naught and A n. Okay, so you simply replay that argument. Instead of using sine mx, use cosine mx. You'll get the formula for an. And if you just use the constant value 1 in this place up here, then you'll get the formula for A naught. Or a half A naught. Yeah. Okay. Okay, I think I might. So I'll just say that in advance of your tutorials, have a go at example 3.4. And look to the first set of exercises. Exercises 3.1. Just there in a couple of pages' time. Okay. Example 3.4, so I'll send a message to the tutors that maybe they can do this in the tutorials if you want. This is to actually verify the claimed Fourier series for the square wave function that we were looking at this morning. Yeah. Or indeed, I'll kick off the next lecture maybe with looking at that. Okay, thanks for your attention. If you got any individual questions, feel free to come up.